So it's my great pleasure to have Lynn Heller here, and she will talk about area estimates for high genus Lawson surfaces. Take it away.
Yeah, hi. Thank you so much for being here, and thank you so much for the invitation and organization of the online seminar. Now it's actually my second talk online, so I have a little experience. So it's very important to say that if you have any questions, since I will have my slides on the computer, or my notes on the computer, I won't see the Zoom. So maybe if you have any questions, don't write into the chat, but rather speak into your phone. And before I forget, I need to say that the thing I'm talking about is joint work with Sebastian Heller and Martin Traizet. And we are trying to figure out how to compute area of the simplest possible minimal surfaces of high genus in S3. So let me say what the setup is. So we start with a compact Riemann surface. So it's oriented of genus G. And the idea is to consider an conformal immersion into the round sphere. And the goal is, first of all, to find minimal surfaces. So that's, if you have a conformal immersion, a solution to Laplace f is 0, and compute the area. And of course, if you can, we can also try to generalize to CMC surfaces. So in a certain sense, these are the best possible realization of your Riemann surface into free space. Okay, so that's how I like to interpret that, because minimal surfaces are also Wilmore surfaces, and those are the roundest possible surfaces. Okay, if you have very simple topology and you restrict to embedded surfaces, there's not much to do. For example, you have a genus 0 and you have a topological sphere, then the only surface you observe is actually a geodesic sphere. And the area is simply 4 pi. And also in genus 1, you have a torus, a topological torus. The only minimal surface you have, which is embedded, is the Clifford torus. Clifford torus. That was shown by Brentle, which was the Lawson conjecture, and the area is 2 pi squared. In those two cases, we have very unique minimal surfaces, and also everything's well understood. And in particular, there's a really complete theory to describe those. So geodesic spheres, well, it's really boring. There's just one sphere. But in the case of a torus, you really have more possible solutions to the minimal surface equation, which are then, of course, not embedded. But then, when the topology gets more complicated, everything gets really difficult. There's only very few examples for G greater or equals 2. And one group of very prominent examples are the so-called Lawson surfaces. And I will draw pictures later, but for now, what you need to know that you give me two numbers, integers, m and k, what you get is one Lawson surface, which is called psi mk, and it has a symmetry group, or the zk plus 1, I would say, times zk and m plus 1. That's contained in the symmetry group of the surface. And in particular, if you can see that from the numbers already, if you have the genus is bigger or equal than 3, then there is more than one one minimal surface. And even embedded minimal surface, because these Lawson surfaces are embedded. And the only other examples you have well known, which are well known, is some gluing examples by Capoleas. What he does is he takes spheres and then glue it together with catenoid handles. So those are very particular examples and very degenerate examples. Others are by Kaja, Pinkai, and Sterling. Also, those uses a geometry, or rather a tiling of S3, and you solve the minimal surface equation only in one of those tilings thing, and then use the symmetries to construct your whole surface. Actually, it's a very similar theory or philosophy as in the Lawson surface case. So what I need to mention is why the construction of these compact minimal surfaces is so difficult. That's because minimal surfaces are real analytic. So if you have one patch of your minimal surface, you cannot simply glue different patches together like what you would do for C-infinity solutions and then have this whole surface closed. But rather you have a patch, it determines already all the surface whenever you enlarge it. So while you have infinite dimensional space of little patches you can use, closed surfaces normally have very, very low dimensions, like minimal surface in these cases are discrete. What we want to study is what happens for G goes to infinity. So that's why my title is really of high genus Lawson surfaces.
So there seems
and
to
for
be a
those,
question, sorry, by Sven.
Yeah.
He raised his hand.
Yes, so what's the relation between G, M, and K?
Oh, sorry, I forgot about that. G is M times K.
Thanks.
Yeah. So we want to discuss the relationship, what happens for G goes to infinity for that, and then of course determine somehow the geometry of the surfaces. Okay, for that we need to draw the picture of how the Lawson surfaces look like. So let me try this slowly. So what you do is first of all to take the stereographic projection from S3 into R3 such that the round tooth sphere in R3 is a geodesic tooth sphere in the S3. And what Lawson does is to choose 4 points on that line here, which is the z-axis, and some points on the circle in the xy plane. So this one, 4 points. Oops. And those 4 points are 0, pi 1. So that's pi 2, maybe better. This is pi 1. And pi 3 is simply minus pi 2. And pi 4 is infinity. And the other points are chosen here along this S1 in the xy plane, which are 2g plus 2 points. So for my picture and for the following of my talk, I will restrict to the case where m is 1 and k is then g. But it works, everything works still for the arbitrary m and k. It's just for the pictures, etc. It's far easier to have it that way. Otherwise, you would have, instead of 4 points here, you would have 2m plus 2 points. So let me, on those points on the circle is called Q's. And they are equidistant. Now, what you do is to take the geodesic foregon, which is given like that, and I hope I just get And those lines are on the S2 I was mentioning, and I just need to erase my picture slightly just to have my foreground here correctly. So that's my geodesic foreground. And what you do is to solve the plateau problem with that foreground in S3. So what you get would be some kind of a surface if you stereographic project it again, like this, maybe. Okay. So now what you see is a piece of minimal surface, and you have two pairs of angles, basically, namely those ones. I hope you can see it correctly. I mean, the colors might be the wrong one. But here, these angles, those are right angles by construction. And then there are more interesting ones for me now, which are those here. These two. They're the same two, and this one I will call rho. And rho is basically 2 pi over 2g plus 2. So this is now important variable for me. Okay, what you do is now the following. For the Lawson surface, you have now a piece of minimal surface which has boundaries. What you need to do is to reflect and to rotate along all geodesics you know, which bound the surface. So these ones, which lies on the S2 and are circles, so, or part of circles, so these are geodesics. These, and also you reflect or rotate along this circle here, and also this one, which is geodesic, or actually a circle in S3. So if you do everything of that, what you obtain is really a closed surface. Let me draw it in another stereographic projection, because then you can see a bit more of the symmetries. Basically what it looked like would be like this. And the 4 points, P1, P2, those will be umbilicus of your surface, and will be like that. So now, why is the surface compact? Maybe it's better to have a top view of the whole picture, just to give you a feeling why everything would close up. The idea is if you have a top picture, the green circle is now my red one, and if you have 6 pieces, maybe that's a 6 hexagon inside here, well, it should be a, well, not the perfect picture. Every edge should be actually the same size, which is not, okay? And you divide it into triangles, which, well, wait, let me have it prepared a bit, which should be really of the same size, really same triangle. And what you do is a plateau problem inside each of these triangles. And the philosophy or the idea is that those angles will be right angles. And if you reflect it, then the surface will be glued together smoothly, so that everything is fine and there's no singularity. But now the tiling is such that everything closes up. And because you do that, now for every piece, everything will close up to really something closed, surface without boundary. So that's the same philosophy as in the Lawson surface case. So what we end up with, in our case of m equals 1 and k equals g, is really a zg plus 1 symmetric surface. And the symmetry axis is this one. And the fixed points of the symmetry are these 4 points. And what you can also see is that the area of your surface is smaller than, or maybe equal 8 pi, because if you have this plane, or this plane will solve the, or that if you just have this part as a piece of a plane, and this part of the surface as a piece of a two-sphere, then it's a competitor for the minimizing the area. So the area of your plateau problem will be smaller than the area of the sphere here and the plane here on this part of the surface. But then if you put sphere here, put sphere here and plane here, what you get is two spheres, and two spheres will be, if you put everything together, have energy to 8 pi, or area 8 pi. So the area of your Lawson surface will definitely be smaller than 8 pi. So that's an easy bound to get, but what else can you say about it? That's a question. And now, what happens for G goes to infinity? So let me just go back to this picture I draw already instead of redraw it. What happens in G goes to infinity is that the angle rho goes to 0. Okay, this is the same thing. That means that we will have extremely lots of lines which will lie on the two-sphere, because those are the lines we reflect along and will stay on the two-sphere. Each time you reflect, you add one line on the two-sphere. So in the limit, it basically, those lines here will basically cover the two-sphere. And those lines, the straight lines down there, those will cover the plane. And if you really do the construction, you will end up with the plane as a two-sphere in S3 and the round two-sphere in R2, which was also a geodesic two-sphere in S3. So what you end up with is two spheres intersecting with right angle. Now, this is maybe not that much of information. Well, it's just a set-wise limit. But what you can do is try to blow up at one of those points, which is one of those intersection points. And what you obtain, if you do that, is that as a blow up, instead of S3 with radius 1, you can look at S3 with radius G, meaning we make the two-sphere we are doing the plateau problem on just bigger. So the polygon is getting flat. And for G goes to infinity, that's my limit, and it will go to R3 in the limit. And the surface, or the point I blow up at, will converge to a Schurk surface, and that looks like this. It will have right angle here. Should be a right angle surface. And let me just try to draw it properly. So it basically looks like intersection of two planes, but instead of the line, which is lies in the intersection, you will have handles. So that's my Schurk surface. It's a very well understood minimal surface. In R3. And it has a known bias stress representation. Just to say, if you don't know anything about that, you have a very explicit parametrization of the surface, and all data is known. And this observation is actually due to Kostner, I should say, as well as the limit that is two-sphere. So now we understand what happens for G goes to infinity. The idea of our paper is to use somehow the implicit function theorem to get from the infinite, or G goes to infinity's limit, and come back a little and construct a surface and then try to compute the area. So let me first state the theorems. So as I said, it's me with Sebastian, since I'm working normally on Wilmore's H², and Martin Traizet. So we can show that if we have a large genus, then we can show the existence of a minimal surface of genus G with symmetry group containing ZG+1. To be honest, this is really not a new result because we will just reconstruct the Lawson surfaces. And also it works for every M and K, just for here. But the new thing is actually in theorem 2 in the same paper, which is the area expands as follows. So that's my limit. So 1, it should be there, but then we have log 2 over G plus log 2 over G² plus something bigger than G cubed. So the approach we use recompute or reconstruct the Lawson surfaces in a way that we have more data of it, namely the area. And the approach we use is called the DPW approach. And I'm pretty sure that most people won't have heard anything about that. So I tried to be, well, very slow on this, or only show a part of it, why this approach is helping us to compute the area. It's due to Dorfmeister, Petit, and Wu, but what I'm showing, or the approach, the gauge theoretic approach to it, is due to Hitchin. So it's not because the DPW, the name is from Hitchin, but just the approach I'm using. And you should think about it as the generalized Weierstrass representation. Basically something saying that whenever you give me 2 holomorphic data, I can give you the surface back, okay? Now, if you have a harmonic map, oops. And we really have a map from M into S3, which we consider to be the Lie group SU2. Then we have a left invariant connection and also a right invariant connection on SU2. And as a matter of fact, the bit difference between those 2 connections is the Maurer-Cartan form. And if you pull back it onto M, it's actually the differential of F in S3. So what it says is basically that F is a gauge between the left invariant connection and the right invariant connection. Okay, and now the point about this is that you can split it into something dz part and something dz star part and put a minus in between, and the area of F is just the integral of the trace phi dash phi tilde. Yeah. So, and this integral actually does not depend on the gauge class of your connections, but because the difference would be, because if you have a flat connection, the difference would be an exact form. If you integrated it, it would disappear. So these forms are really the quantities you're looking for if you want to compute the area. And
sorry, may I interrupt you? The formula for the area should have an O of G to the -3, right? 1 over G cubed. Yeah.
1 over G.
Okay, Thanks.
No. Sure. So it don't need to tell you anything of this. The point is the phi is the measure I want to have, or the quantity I want to compute the area, okay? And luckily, the DPW approach actually just compute phi, okay? That's my message here. We write down connections, and that's not the usual way to denote them, but I don't want to introduce too many things. This one is a one form with values into the endomorphisms, a small SL to C if you want. It just has DZ parts. So it's basically phi if you want to, or you can think about it as phi. And it's a holomorphic one form. Also eta is a holomorphic one form. And the lambda is in C star. The idea is that nabla 1 is gauge equivalent to the left invariant connection, and lambda minus 1 is gauge equivalent to the right invariant connection. And given such a family, so a C star family of flat connections, we can reconstruct the surface by doing, or by requiring three properties. First of all, the asymptotics at lambda equals 0. It should have a pole-like singularity at lambda equals 0. Second, it's unitarizable for lambda in the unit circle. And third, the one which corresponds to the left invariant, right invariant connection should be trivial. These last two, this is called solving the monodromy problem. And the second one can be interpreted basically as a local or intrinsic closing. So that the curvature terms all close are periodic solutions on M. And this one is an extrinsic closing, that the surface really close up in space. Now, it doesn't give you a reconstruction formula right now. How does that work? Solve the following. We solve a differential equation for some matrix psi. So it should be a fundamental solution to your ODE. And the second is factorize the solution. In a way such that F lambda is SU2 for lambda in S1. That was the condition unitarizable. And this B should be positive, which means extend to lambda equals 0. And these B's are really, if you go back here, the gauges I was considering. So this one is B1, lambda 1 is a gauge equivalent to the left invariant connection by B1, and this one is really B minus 1. Or maybe, well, it should be not inverse, right? So that how you get from the DPW potential the surface. Now the idea is, of course, to reconstruct or construct a family of DPW potentials solving all these properties. But by doing that, what you get is really, you compute this eta lambda, and actually the phi's, which you need to compute the area. So that's the basic or the major improvement here. Now, solving the monotony problem is of course difficult, because whenever you have so unitary connections, it's very hard to get, and then if you do that, you still need the trivial connections on these 2 points. And so for the torus case, we really have a complete theory of how to do that. But for higher genus cases, there has been no systematic approach, and actually these are the first surfaces ever constructed with such an approach. But the idea of how to construct DPW potentials with all these properties is pretty simple. Start at some well-understood surface. And then deform it, or deform the respective DPW potential in direction of compact surfaces. Which are all, of course, along the way, you solve all the properties, and what you get, the surface you get back is really minimal or CMC. Which are minimal or CMC. And of course, we want to solve it via some implicit function theorem. Now, you might ask, how would that work? Because G is some integer number, and you want to use some kind of a flow to deform something, well, integer-like to some other integer, which seems not to work. The idea is to relax a bit of the closing conditions. Basically, you cut your surface open and then bend it open. So most of the time, it will not be a closed surface. But whenever T is rational, you get a closed surface on some multiple cover of the surface. So the idea, we had the idea in a joint paper with Sebastian Heller and Nicholas Schmidt, which is published 18. And we started there at stable homogeneous tori, and also maybe 2-lobed Delaunay tori. So stable homogeneous tori are simply those which are rotation of a circle, and circle should be not too small. And what we obtain are high genus minimal surfaces. And also that works also for CMC surfaces, but with branch points. But exactly at those 4 points I showed you before, which are the fixed points of my symmetry. And Martin did a very similar work actually for enoids. So start at a sphere and add handles. So what he does is he started at a sphere and with some points and added here catenoidal handles to it to obtain, etc., to obtain enoids with G ends or more ends, which is CMC surface in R3. And his approach is such that this don't need to be symmetric. So what we did was to put all these ideas together now to obtain really a compact surface, minimal surface, and smooth one without branch points in S3. How does that work? So instead of starting at a homogeneous torus or at a sphere, we start at a point. Well, it's a dual surface of the sphere, so basically it would say maybe a sphere. And then go in direction of the sharp surface. Which was the blow-up limit of the Lawson surfaces if you blow it up by genus G, right? And then use symmetry. So how does this look like? Let me just draw a picture. And again, this is just a genus 2 surface with these handles. And we have the symmetry line here, which will have 4 fixed points. What we do is to cut out the handle. From the side now, this would look easier. It's just really some handle of half of a donut maybe. And those are the 4 points, which are fixed points of the symmetry. And now we identify these sides, and we end up with a sphere with 4 points on it. Now, the key point of it is that the monodromy of my connections I want to construct will have local monodromy rho, which was given by the angle of the geodesic foreground, or just 2 pi over 2g plus 2. So it's independent of the covering you choose in a sense, and also it's the same at all 4 points. So now the rho goes to the zero, goes to the rho limit needs to be considered, but the key point here is that we don't go to the cover. We have the same domain for every surface. And actually everything makes still sense is if rho is not 2 pi over 2g plus 2, but for every real number. The only problem is for general real number, you cannot go upstairs and get a closed surface, but it doesn't matter. You still have your handle, which you can construct. It's just if you take the analytic continuation, you would close up, but that's an okay thing. So after that, what you do is you take a proper ansatz. For the potential. With T is basically equals. Maybe there's a factor 1/2 missing here. The potential will look like, let me just write it down first and then explain what this means. So this one is actually the potential of the point. It's a constant. It's almost 0 for the 3 components here. It's matrix, right? And here's just some constant. And those are the initial conditions, or actually the sharp surface. So without the T. So that's basically what it means. You start at a point, and then T times, in first order at least, is the sharp surface. Now, the parameters for the implicit function theorem is then the following. We have the coefficients of the point potential, which is just one constant. So it's just one constant. And then the coefficients of those AI lambda was still there, which are small SL2C matrices. And by chance, well, not by chance, but these little functions here, those are simply holomorphic functions in lambda, but does not depend at all on the surface. So it's really just some polynomial or power series in lambda. So A, B, and C are power series in lambda. And of course, at t equals 0, we exactly know what these should be, actually degree 2 polynomials. So as I said already, that we wanted to use implicit function theorem to solve the monodromy problem, basically keep the monodromy in small SU2. So basically, so A plus A star is 0, A bar star is 0. So that's the condition on which we use the implicit function theorem. We show that you can do that, okay, that the differential is surjective, etc., and the result, and let me end by this, is the DPW potential in T. And from that, because it's just a gauge away from the phi I was considering before, in which the area is given, and from that here, it's easy to compute, or it has the same degree of the area, or the expansion of the area. So that's all I had to say. Thank you.
Thank you very much. Other questions, remarks, comments? I hear somebody.
Okay. I have a question.
Hi, Carsten.
Hi. For talk, I think you said this works for any pair of MKs. When you state your theorem, you had M equals 1, right?
Yeah, it works for everything.
But so there's a similar expansion for
Exactly.
For the MK case, yeah?
Yes. Mm-hmm. You, of course, you start also as at a larger sphere, so the first factor also changes, right?
Yeah, sure.
Instead of 2 spheres, it would start with, and then, yeah, sure.
M spheres, yeah?
Yeah.
Okay, and is the second question, is the area expansion what you expected? Or, I mean, this factor, what is it, logarithm of 2
log
times, log 2 times g minus 1 over g squared? Is this what you expected, or is it?
Well, it's definitely I had no expectations other than that the first degree should be negative, right?
Sure.
It should be decreasing to a positive number. So this one is something that the sign of this is expected, but what kind of number it is, it's not. And for example, for the Capillea surfaces, Rob told me that it should be 0, and I think we almost can show that. Yeah, so this will have lower energy than a Capillea surfaces if you just group in with catenoidal handles, yes.
Mm-hmm. Thank you.
Further questions, remarks, comments? There's one.
Hi. Yeah, I'm. So it seems that the starting point of your construction is really the DPW data for the Shirk Tower, and
yes.
Basically, does the same process carry through if you know the DPW representation for another classical minimal surface you can use as a building block?
Sure. I mean, this idea works very generally. So whenever you know a surface very well and know enough data, then you can do the same process. But, well, the only thing is until now, we need some kind of symmetry to reduce it to some common domains for all genuses or something. So we normally use only part of the handle such that, you can really go back to the same domain and you really have a smooth parameter on the same domain, etc.
Yeah.
But without that constraint, basically, this idea works really very generally. Yes.
Okay. So can you imagine doing a similar estimate when you have, say, a sequence of minimal immersions in the two-sphere, which are essentially intersecting geodesic spheres, where the intersections are great circles are great circles, and then when you perturb off that, you obtain towers of shirks intersecting at some angles.
Yeah, that's something we have done. Okay, that's
Okay.
just MKKs, so that's working. There's not that much limiting surface you can expect, because there's this shirk uniqueness conjecture which says that, well, for at least if it's the number of intersecting spheres is 2, you can only expect as a limit surface a shirk surface or a catenoid. So there's only that much of limits possible for 2 spheres. So that's definitely something you can investigate. And I think for higher thing, or more spheres intersecting, there must be similar conjectures. So actually the possible directions you can go is very, very limited.
I see. Okay, thank you.
You're welcome.
Further questions? Remarks, comments? That seems not to be the case, so let's thank Lynn again.